Hi there, everybody. Welcome to our vodcast on the motion of the Earth. Now, the two motions that we're going to talk about is the rotation of the Earth and the revolution of the Earth around the Sun. So let's get started. The first motion that we're going to talk about is Earth's rotation. Now, Earth's rotation is defined simply as the spinning of the Earth on its axis. So you can see the rotation of the Earth right here. All you see is the Earth just spinning in place around this imaginary line that runs through the middle of the Earth at a 23.5-degree angle called its axis. And usually we identify the top of the axis with the North Pole and then the bottom of the axis with the South Pole. And as you can tell, that central line is the line that cuts through the middle as the Earth spins. Now, it takes a certain amount of time for the Earth to complete one spin, and that's called the period of rotation. If you have trouble remembering that, think about your class periods. Your class periods are chunks of time designated for certain subjects. So period 1 is a 40-minute block of time for one subject, and then period 2 is another designated block of time for another subject. Well, your period of rotation is a block of time for the Earth to spin once, and we could describe it several different ways. It actually takes the Earth 23 hours, 56 minutes, and some change in seconds to complete one rotation. However, we round that up to 24 hours because it's easier, and as we know, 24 hours is equal to 1 day. So it actually takes the Earth 1 day to complete one spin. So when the calendar switches over from Monday into Tuesday, the reason why it goes from Monday to Tuesday is because the beginning of Tuesday marks one complete spin of the Earth. And then Tuesday to Wednesday is another complete rotation of the Earth, and then Wednesday to Thursday is another one, and the Earth will have 365 and 1/4 rotations in a year. If you take a look at this diagram here, or this animation rather, you'll notice that the Earth spins in a particular direction, and you'll also notice if you look that the land masses start from the west and go east, west and go east, west and go east. So you could probably tell that the direction of the rotation is from west to east. And if you take a look at this rotation from above, the North Pole, you'll see that it goes in a counterclockwise direction. Now, the rotation of the Earth is going to affect the path of the sun across the sky, and that affects where the sun rises and the sun sets. So because of this counterclockwise west to east rotation, our sun is always going to rise in the east and then sets in the west. Let's take a peek at how that looks on Google Earth. So let's start out with some basics here. The bright half of the Earth is in daytime, so because it's getting the sunlight from the sun. The dark half of the Earth is nighttime because it's getting no light from the sun. So currently, the United States is in nighttime, and then you have Europe and Asia in daytime. Now, the Earth, remember, rotates in a counterclockwise direction, so it moves in this direction here. Keep an eye on the eastern coast of the United States. As the Earth rotates in its counterclockwise direction, you're going to notice that the eastern coast of the United States is going to get to the sunlight first. This is going to give us the apparent motion of the sun rising in the east and starting to move across our sky. So why does the sun rise in the east? Well, simply put, because the eastern part of the country is going to get to the sunlight first. And as a result, that sun is going to rise and then move across our sky as the Earth rotates and spins in front of the sun, and now we are in daytime. And as we continue to rotate, the sun will move across our sky even more and start setting into the western part. And the reason why it appears to set in the west is because if you take a look, as the eastern coast enters nighttime, the last bits of sunlight are located in the western portion of the United States, giving us the apparent motion that the sun is setting in the west. And eventually they will catch up and then be in nighttime again. So that's why the sun appears to move through our sky. Now, this is what it kind of looks like throughout the day. If over here on the right is the east, and then over here on the left is west, our sun will rise up in the east and then get to a peak point at about noon in this area and then start to set back towards the west. So we have that apparent motion. All right, so that's rotation of the Earth. Now let's talk about the evidence to help prove rotation of the Earth. Now there's two pieces of evidence that we're going to discuss. First piece of evidence are star trails. Star trails are these circular trails that the stars leave when exposed or overexposed to a camera. The reason why the stars leave these trails is because throughout the night, even though we can't see it, the stars actually appear to rotate in the sky above us. However, it's not the stars that are actually moving, it's actually the Earth that's moving underneath the sky. So as the Earth spins underneath the sky, these stars appear to spin in our sky. Basically like this. If you were to stand up right now and look at your ceiling and then start to rotate in place, your ceiling will appear to be spinning above you. But as you know, the room is not actually spinning, you are spinning underneath the ceiling. So your rotation in place gives the ceiling an apparent motion of rotation. That's the same thing that happens with Earth. The stars don't rotate around us in the sky, it's that the Earth rotates underneath the sky, giving our star trails here. Now, a second piece of information or second piece of evidence to help prove this is what we call Foucault's pendulum. Foucault's pendulum was designed and set up in 1851, and it was the first thing that really gives us any simple evidence that the Earth rotates. And all this pendulum does is swing back and forth, and it knocks down these pegs. All right, so here we have an example of Foucault's pendulum. So once I set this in motion, you'll see that the pendulum swings back and forth, and the pendulum would hit about here, okay, right above this dot. However, since the Earth rotates and the board below is attached to the Earth, it's going to start to move, and you'll see that 30 seconds later that the position of where the pendulum hits has now changed. It's no longer over here, it's slightly more to our left. And that's caused by the rotation of the Earth moving this board. And as the Earth continues to rotate, you'll notice that it's now touching the peg. And at about 90 seconds later, after we started, this pendulum is going to come swinging, and it's going to knock down the peg. And the reason why that happens is because the Earth was rotating underneath the pendulum. If the Earth did not rotate underneath the pendulum, then the pegs wouldn't be knocked down. And that's why when you take a look at this picture here, you'll see these sets of pegs knocked down here, and those sets of pegs knocked down on the other side, on the opposite side. So that's Foucault's pendulum, and that's Earth's rotation. So why don't we just take a quick look at what Earth's revolution looks like. Now, Earth's revolution is a little bit different from the Earth's rotation, because Earth's revolution is not the spinning of Earth. That's the rotation. The revolution of the Earth involves the movement of the Earth in its orbit around the Sun. So when you take a look at this diagram down here, you'll see our inner planets, Earth, Mars out here, Mercury, and then Venus, and then in the middle is the Sun. As you can tell, each planet has an elliptical type shape going around the Sun, and those are the planet's orbits. Here in the green is Earth's orbit. So this is the path that the Earth takes around the Sun. So as a planet revolves around the Sun, it just simply moves around it. That's all. It's just traveling through space in its orbital path around the Sun. Now, our revolution, or period of revolution, remember, is the block of time it takes for the Earth to go around the Sun. It takes us 365.25 days to do this, or as we like to call it, 12 months, or we call it 1 year. So for the Earth to finish one complete revolution around the Sun, it takes us 1 year. So you could think of it as New Year's. Whenever you celebrate it, you're celebrating a safe trip around the Sun and then the beginning of a new one. And then lastly, the direction of revolution. As you can see, the planets are moving again in the opposite direction of where the clock hands would go if this were a clock. So as a result, the direction of our planets for revolution would be counterclockwise. All right, so to sum up Earth's revolution, it's the movement of the Earth in its orbit around the Sun. It takes us 1 year to do it, or 12 months, or 365.25 days. And then the direction, just like everything else, is counterclockwise. All right, so that concludes our lesson on rotation and revolution of the Earth. I hope you found that helpful. Thanks for tuning in.